So I want to talk a little bit more about the geometry. And again, we'll talk a bit more about geometry too on tomorrow when we talk about multiple surfaces. So again, we've got a lot of concepts that I'm trying to build them up relatively slowly. So I want to talk about Landy-Arnold quadratic regressions. I want to talk about mean standardization and fitness elasticity. Talk about problems with the quadratic regression. One category is exponential fitness functions. Another category is non-parametric estimators. I want to talk about generalized selection gradients, and then talk about dealing with non-Gaussian residuals. So a word on this. When you fit a regression, I'm predicting fitness as a function of phenotype. That residual there, in normal regression theory, that residual is a normal. That's a bad assumption for fitness data. Why? Fitness data can be heteroskedastic. If my fitness data are survival probabilities, those residuals are going to vary as my survival probabilities vary. Another big problem is fitness data usually has a big point mass at 0. Things that don't leave offspring for whatever reason. So a fitness residuals are almost never normal, and so more models which better capture the appropriate distribution give you a bit more power, and Astra models do that, and we'll talk about that to some extent. So mainly talking about geometry here. And let's go back and look again a little bit at that Landy-Arnold fitness estimation. So I can basically write a regression. Fitness equals some constant plus B1 times my trait value plus B2 times my trait value squared, or maybe the square root of my trait value minus means. They're essentially the same thing. You can then go through and look and see what those expressions are. When you actually work those out, you get these complicated expressions here. If you have normality, these simplify. So under normality, skewness is 0. So that term is 0, that term is 0, that term is 0, that term is 0. And for example, if these terms, if skewness is 0, those cancel. And what am I left with? S over sigma squared z, that's beta. If skewness cancels here, I'm now left with this expression here. And in the case where you've got normal variances, this becomes c over sigma to the fourth, and you get the result that you want before. So if you have normality of your trait, remember, normality can come in terms of how the trait is distributed, and normality can come in when you fit the regressions. Once you fit fitness, what's the residual look like? So normality in terms of trait values, that's pretty easy to check, usually okay. Normality in terms of fitness distribution, fitness residuals, usually violated. But here, I'm simply using normality in terms of trait values. And what you can basically show is that if normally distributed, then you've got these relationships here. Skewness is 0, and this is simply a measure of their kurtosis. And the net result basically is you can then write the Landy-Arnold regression in this form, where I simply put in the intercepts. I could then simply call this beta times z plus gamma over 2 times z squared plus some constant. So this expression here is called a Landy-Arnold regression, and most of estimates of fitness in natural populations with traits since this paper come out report Landy-Arnold coefficients. I mentioned that beta is the term on the linear regression, and gamma, in this case over 2, is the weight on the quadratic regression. Now, these were actually worked on before Landy and Arnold. Remember I told you about Weldon's data? Well, Pearson was the person that worked with Weldon. You might remember Pearson product correlation coefficient, this guy. So Pearson actually was one of the first people to look at linear algebra in terms of these regression equations, and therefore this is occasionally called a Pearson-Landy-Arnold regression, because Pearson 1903 had these sort of things. We can then write this in what we call standardized form. Standardized form is different from a regression package. In a regression package, standardized form says take your predictor variable, subtract off its mean, and express it in terms of standard deviations. Check, we've done that. But it also says take your other variable and standardize it by its variance once you adjust that. Here, our standardization is mean standardization because we take W, the big W, the observed fitness, and divide that by W bar. So the W variables are standardized by using means, and the standard Landy-Arnold fitness estimation, the trait values are typically standardized by subtracting off the mean and dividing by the standard deviation. That gives these mean 0 and variance 1. If you don't have normality, that term there is given by this. If you don't have normality, so remember, basically, that part of the term there is beta. But if you don't have normality, if you have skew, these terms take that linear term and move it away from the value of beta. So if you don't have a trait that's normally distributed, you get a scenario where the quadratic term is correct. It's gamma over 2, but the linear term is something different from beta. So in that case, what you'd first do is fit a linear regression. That linear term is beta, then fit a quadratic regression, and that quadratic term there is given by gamma. Okay, so you see that in literature sometime, and that's the point we'll come back and talk about it. And this actually points out that a slightly cleaner way to do that if you don't have normality is to fit a straight quadratic regression, no linear term, and you can get a slightly improved estimator of what gamma is. That's a detail. Just be aware of when your fitness distribution, when your trait distribution is not normal, the coefficients in the Landy-Arnold quadratic regression you need to pay some attention to them. That's the main point to take away. And you can look in the book and see what those details are. I'll skip those geometries because you said that before. So you basically have the geometry determined by the best quadratic fit and the best linear fit. And that's independent of what the actual fitness distribution looks like. You're taking an arbitrary distribution and asking what's the best linear fit, and also asking what's the best quadratic fit. We'll come back and talk about what happens how good is that best quadratic fit if you've got nonlinearities. We'll talk about in a second. I want to talk about another point that was raised, and that is we usually express the trait values as variance standardized. So beta would be the mean, would be the expected change in relative fitness for a 1 standard deviation change in the trait value. Another approach, which is what we do with fitness, is to mean standardize. Under mean standardization, beta would be the expected change if I change my trait by its mean. So why do we use one versus the other? And this gets into a debate about mean standardization and variance standardization. And David Hull and Thomas Hansen were a lot of the people, especially initially David, that worried about variance and mean standardization. And it traces back to heritability. Heritability is additive variation divided by total variation. If you do that, the heritability for fitness traits tends to be small. Heritability for morphological traits tends to be large. But David said, what if instead of variance standardizing, we mean standardize? So he called it evolvability. Additive variance divided by the mean squared, or the coefficient of the additive variance, the square root of additive variance divided by the mean. When you mean standardize, you see something rather remarkable. And the rather remarkable thing you see is that mean standardized variances are larger for fitness traits than for morphological traits. So the reason heritability goes down is for fitness traits, you also inflate the residual variance dramatically. And that heritability is additive over additive plus residual. If that residual goes up, even if the additive variance goes up, that overall ratio goes down. So there's a long debate that goes back and forth about mean standardization and variance standardization. The nice thing about mean standardization is it talks about proportional changes. So if you mean standardize, you can ask, how much do I have to double the character value? If you variance standardize, you can basically ask, how much do I have to change it by a certain standard deviation? On some level, variance standardization is not a natural scale because that variance can change, whereas mean standardization is. How much do I need to double the trait value? So there's a large debate that goes back and forth about mean and variance standardizations. A lot of that's talked about in chapter 6. It's also talked about in the first book. But the basic idea is I could use mean standardization. And under mean standardization, this is now the interpretation. So if I take a beta unstandardized and multiply it by the mean, that gives me the beta under mean standardization. This idea, mean standardization, goes back at least as far as Johnson in 1955. So why might you do that? Well, here are relationships between unstandardized, that's variance standardized, that's mean standardized. You can relate them. One of the reasons to use mean standardization is if you look at what the if the trait is fitness itself, then under mean standardization, beta has a value of 1. So you often ask how strong selection is. If you use mean standardization, you have a natural metric. A beta of 1 says that trait's as strong as selection. By the way, you can get betas bigger than 1. That simply means you have an extreme increase in fitness in some small area. It's nothing to worry about too much. You can also get it from error in there. The other thing you can ask is what's the proportional change in the response? And that equals this term here, which is evolvability, basically additive variance divided by the mean of the character squared times your mean standardized variance. So evolvability times mean standardized variance tells you what the expected fractional change in the value of your character is, not the change in terms of standard deviations. One concern is that the trait has been under a long history of selection. A lot of its additive variation may be eroded away, so it's got a tiny additive variation about it. And therefore, a 3 standard deviation change sounds like a lot, but it's actually not much of a change in terms of the trait value. So if you talk about proportional change, what fraction of the mean is the response, using mean standardization is how you basically express that. So we have mean standardization and variance standardization. Mean standardization has some nice properties, such as a beta that's mean standardized. You can compare that to 1, which is the standardization if the trait is fitness itself. But it also has another really interesting, deeper interpretation. This gets back to the notion of elasticities. Remember we talked about I had a Leslie matrix. What happens if I perturb elements in that matrix? So I perturb the survival from stage 3 to stage 4. I perturb the number of offspring in stage 7. How does that change the overall population growth rate? And more generally, of course, how would that change fitness? Well, that derivative of that term of lambda, the overall growth rate, with respect to that term, we call that the sensitivity. A better measure is the elasticity, which is derivative of log of that term with respect to log of that value. And the elasticity talks about a proportional change in the overall fitness given a proportional change in the component. And that's the expression there for elasticity. And what you can show is when you mean standardize the gradients, that's the equivalent of an elasticity. So mean standardization have this nice feature, and they can basically tell us about how sensitive changes are in terms of changing relative fitness. So for example, if the mean standardization is 0.3, doubling the trait value increases fitness by 30%. If with variance standardization, if the gradient is 0.3, it means a 1 standard deviation change results in a 30% increase. Standard deviations don't tell you much about the actual trait value, so often we're interested in proportional changes, and likewise the mean standardized gradients can be related to elasticity. Let me show you why that's important. So suppose I have, what I really want to know is how does the overall growth rate change when I change the mean of a given trait? Well, you can imagine that trait influences several episodes of selection. The simplest is it influences reproduction and influences survival. So this expression here says, this is the elasticity of overall growth rate with respect to fitness component I. This is the elasticity of fitness component I with respect to change in that trait. And I can simply write that as elasticity of fitness component I times the mean standardized gradient of the trait. Again, as always, I stress, the important points to take away is the general feel, because the details may be fairly new and they may be kind of hard to grasp. If you take away the general idea that mean standardization may sometimes be important and it's related to sensitivities, then you can go and look up in the chapter in the original papers and kind of follow through it in a bit more detail. So let's give an idea about, and we'll see this in elasticity path analysis tomorrow, but here's an example of that. So here are some data for an avian data set. What they found was the mean standardized gradients for viability for an average trait was about 0.57, and fecundity was about 0.23. In an avian data set, they basically found that the elasticities for viability on overall growth rate was 0.6. For fecundity on overall growth rate was 0.25. So these are the elasticities of viability on growth rate, fecundity on growth rate. These are the elasticities of trait means on viabilities and trait means on fecundities. So you put those together, what you can basically then ask is, what's the change that occurs via viability selection? Well, you can multiply elasticities here. So this is the elasticity of viability selection on growth rate. This is the elasticity of changes in the trait on viability selection. That gives you a value of 0.34. You do the same thing for fecundity. That's the elasticity of fecundity on growth rate. That's the mean standardized gradient. That's the average elasticity of a fitness mean on fecundity. You get a value of 0.6. Add them together, the total elasticity is about 0.4. The vast majority is due to the fact that traits changed viability, not fecundity. And these elasticities allow you to basically decompose for your particular trait what the impact on overall fitness is, if that impact is more on fecundity or viability. A nice data set summarized by Krohn across a variety of studies showed adult viability usually had a higher elasticity on fitness than fecundity. So a lot of people measure fecundity, lifetime reproductive success, as their surrogate measure for total fitness. What this paper suggests is that viability is actually a better predictor of lifetime of overall fitness than is fecundity. One exception was the group of plants that have a single episode of reproduction before death. Here, growth rate had the highest elasticity, followed by fecundity and adult viability. Why? Because growth rate determines how big you get before you flower. So all else being equal, traits under viability selection likely have a larger impact on the overall population growth rate than do traits under fecundity selection. So this sort of analysis shows how you can connect ecological things in terms of how do different components of life history change your overall fitness with traits. How do changes in different traits affect individual life history components? Life history components on overall fitness are elasticity. Traits on individual life history components, those are mean standardized gradients. Those are also elasticities and allows you to connect those. And we'll talk about elasticity path analysis tomorrow, which is another way of putting these features together. So again, it's another tool in your toolbox to look at sensitivities and to try to connect ecological issues with trait issues. Okay? So that's mean standardization. The advantage of mean standardization is a amount to elasticities, which give you this nice property of asking what their impact on total fitness is through various fitness components. Mean standardization is also nice in that if you have fitness itself is the trait, its mean standardized gradient is 1. So you can ask about the relative strength by comparing your mean standardized beta with the value of 1. And finally, mean standardization is nice because the notion of evolvability. What fractional change in the trait do I see is often as natural or more natural of a metric than asking how many phenotypic standard deviations it changes. Let me give you one more point, and then we'll see if there are questions. However, as with everything, there are some caveats. And the caveat here is if a trait has a biologically motivated zero value, height, etc., then if you have, you can use mean standardization. If the origin of traits is arbitrary, such as the calendar date, that's arbitrary, or composite traits, principal components, then mean standardization is really not defined. So it doesn't work on all characters. It has to work on characters which have a natural scale that is a natural zero. Now, how you scale away from zero is different. You could scale inches or miles, but they have to have a natural zero. Otherwise, you can't do that. There's also an interesting issue. So, for example, suppose I looked at resistance fraction and the susceptibility fraction. Either can be used as a measure of strength of selection, however, if you use mean standardization, these things return different gradients unless f equals a half. So for some traits, you've got this asymmetry. Finally, Kingsolver et al. Noted that traits with large mean standardized values tend to have small coefficients of variation. So there's a tendency for these to say something about the variance as well, and that trend wouldn't be expected if it's a fair standardization. Not that it's in the direction, but you wouldn't expect any trend whatsoever. And the fact that traits with large mean standardized values tend to have small coefficients of variation says that maybe other stuff is going on. So as with anything in your toolbox, there are nice uses of it, but there are also times where it's not appropriate. So how do you proceed? Well, very often how you proceed is you do the analysis using this and using mean standardized and variance standardized and ask how consistent your results are. If they're rather consistent, okay. If they're rather inconsistent, then that tells you something about your system as well. So even in cases you might ask, which do you use? If you have to ask which should you use, the obvious answer is use both and look at how consistent the results are. And if they're not consistent, ask what that tells you about your system. Okay? So that's what I wanted to say. Make sure it's everything. Yeah, that's what I wanted to say about variance standardized gradients. They're another way of standardization. They have some nice features when you can apply them. And for that reason, some people prefer them. In your analysis, it probably makes sense if there's a natural mean of zero to use both and look at what the interpretations of both are in your particular problem. So questions or comments on mean standardization? It sounds like a technicality, but it actually can be rather important when you kind of get down and look at the nuts and bolts. So be aware that it's out there and be aware of where to look it up. Yes? Trying to think about that. You caught me off guard. My initial reaction would say you can do it, but no, I think it goes for traits bounded above by zero. You thought about this a bit. What's that? No, but I mean, can you get negative values? If you have traits which can get negative values, can you mean standardized? I think the answer is no, right? Yeah, no. Oh, I see. Gotcha. Yes, that's how you get around that scale. But that's for evolvability. For mean standardization, so I think you have to have positive means. I'll have to think about that, but you caught me off. That's a good question. If I had to bet, I'd take my dollar and I'd bet 55 cents on you have to have positive values, and I bet 45 cents, on some other answer. Good question. Yes. Absolutely. Yeah, absolutely. Sure. Well, so let me phrase it the other way around. Why are you using variance standardization? So if which you set as the null, if you set mean as the null, then you have to argue why you have to variance standardize. If you set variance standardization as a null, you have to argue why you have to mean standardize. I would argue that you're a priori, if you've got a natural scale of 0, and let's imagine now the traits take on positive values, that your natural thing would be to consider both of those equally. That is, if you can't mean standardize, there's no natural 0, then that's fine. That's default for variance standardization. But otherwise, what's your advantage for variance over mean? And people often say, well, we always variance standardize. Therefore, you've got to show me why to mean standardize. But in fact, that's just a convention. Mean standardization might be better. Again, the answer is not either or, the answer is sort of both. Sure. You certainly have to, no question you have to standardize, absolutely. Your point isn't how you standardize. Your point is, should you standardize? Well, standardization is nice in that it allows you to make comparable statements on different characters. Now, if you variance standardize, the statements are based upon standard deviation changes. If you mean standardize, they're based upon mean changes. Those could be different things depending upon your scale, but you've standardized, and you're talking about fractional changes in mean and fractional changes in added variance. Sure. Right. Sure. Right. But then when you transmit back, you then get expected changes in terms of phenotypic standard errors, which you can then translate into actual values. So, I can actually tell you how many inches this trait's going to, what I predict, how many inches this trait will change. You feel it's what? What you're doing in both cases is predicting constraints which are there. And remember that what happens is if you have traits with high variance, it will shrink their beta values when you standardize them. So it all comes out in the wash. And there are advantages using correlation matrices, because with the correlation matrices, there's nice expressions for the spread in the eigenvalues. Because the correlation matrix, it's n by n, the trace is n, so the sum of the eigenvalues is n. And basically you can ask about dimensionality by looking at what your spread in the eigenvalues is about that. So there are advantages with correlation matrices as well. The bottom line, good point, is if there was a button you push that did your analysis, you'd be out of a job. So these are things you have to consider, and I'd recommend going back and reading a couple of papers by Poole and Hansen, where they talk a fair length about rationality for standardization, not standardization. Now, they're coming from a particular standpoint, but it's still good to sort of read those papers. Your point about you should think before you standardize is a good one. But oftentimes when you think before you standardize, it makes sense to standardize. You don't have to, but you should. Maybe the best way to ask yourself is, why should I not standardize? So you make standardization the default, but don't make it the 100% default. I think that's a good place to start from, because you're less likely to make errors. If you start from, I'm not going to standardize, I'm going to standardize, then ask, okay, are there reasons why I should standardize, either mean or variance? I think that's probably a good way to proceed. Yeah. And your traits will be a mixture of both. If your traits have some that you can't mean standardize, there's no natural 0, then you've got to, by default, variance standardize all of them to treat, because if you put them in the regression, Yes, but I think what you end up doing is variance standardizing your quadratic terms. I think that's how you get out of that. So so basically for your quadratic term, what you're looking at is z minus mu squared. So when you standardize that, its expected value is the variance. Right? I think that's the, just thinking about it on the fly. I think that's the way around that issue. But again, the bottom line is there's issues about standardization and what standardization you should use. It's not cut and dry. So be aware that those issues are out there. So the other thing I want to talk about, two other things, are quadratic and problems it may or may not cause, and also how you handle non-normal residuals. So here's the key point number 2. Quadratic surfaces can be very misleading. If I have a quadratic surface, it forces me to only have one maximum or minimum for a single trait. For a bunch of traits, it forces me to have only one extremum, a saddle point or a local minimum or a local maximum. I can't have a multi-peak surface if I force a quadratic. So if I look at a small enough window of the individual fitness space, that might not be a big deal. If my data span a certain amount of the individual fitness space, I may have multiple peaks, and we'll see examples of that next time. So this basically says just what I said there. So Tom Mitchell-Olds, and again Ruth here, had a couple of very influential papers where they basically talked about the problems with fitting a quadratic regression to data. And here's example number 1. The dashed line is my distribution of the phenotype. I have truncation selection. Only individuals above this point are saved. So my fitness function is 0, flat line here. My flat line is arbitrary. When I go ahead and fit this data, so basically I've got fitness 0, fitness 1. So run the numbers up here, run the numbers down there. When you fit the best quadratic, you get this. You get a minimum that's introduced. And depending upon where you pick this, you can get maximums, etc. So here, truncation selection, the best fitting quadratic curve would suggest you've got disruptive selection. That's misleading. Here's another example. Here is impatience. Here are late growth rate compared to relative fitness. And if you fit these data with, it's obviously got a nonlinear term. So if you fit a linear term, you get a good fit. You then ask about a quadratic term, you get a significant quadratic term, you get this little bump up here. When in fact, when Mitchell-Olds fit these data, he found this curve was better fit not by a quadratic, but by this exponential term we'll talk about in a second here. So exponentials, typo, let me fix that. See, should be a superscript. Oh, okay. It says it's a superscript, sure doesn't look like it. No, anyhow. That should be z squared. Not sure what it doesn't look like it. It says that it is, but that could be the issue. Okay. That will fix it. I'll take care of that. Thank you. Here's another example. The solid curve here is the true fitness function. You've got stabilizing selection, but your population mean is off to one side, so your best fitting curve through that gives you this. It gives you an upward curve, not a curve with a downward trend, even though the data you're coming from, basically the fitness function curves downward. The problem is most of your sample points are over here, so when you fit over there, you basically fit a curve that's consistent with an upward curvature, not a downward curvature. So even in a scenario where you have a single mode, depending upon where your data lie, your quadratic fit can be misleading. Why is it misleading? Because that's not a quadratic curve, that's an exponential curve. And if it tries to fit that, it'll fit something a little bit differently. So there's a couple ways to get around that. One way is to look at another form, exponential forms. The problem here, of course, is these things also only have a single minimum or maximum. Then we'll talk about non-parametric methods, where you assume no functional form and try to fit those. Here is the classic Gaussian fitness function. Weldon was actually the first to use this. What this basically says is your fitness curve is a bell-shaped curve. And Weldon actually showed that his crab data looked like this. The bell-shaped curve has a peak. That peak is right on the optimal value. And the width of that curve, the variance, tells you the strength of selection. If the variance is small, selection is really strong because you fall off quickly. If the variance is large, selection is weaker because you have to fall off a larger distance to get the same fitness effect. So these are ones that you can use. That's a natural other curve to fit, but you can also modify strictly directional selection by this exponential function here. As long as beta is not too large, this is linear with a little bit of an upward curve. You can then put them together and have this much more general form. And in this more general form, you can have directional selection, stabilizing selection, or disruptive selection. So again, there's a constraint here in that you can only have one maximum or one minimum, but it's a different type of functional form you can fit the data to. And so, for example, over here, that's actually better fit by this exponential curve than it is fit by assuming a quadratic. So that's one scenario you can use. The other scenario, and Dolph Schluter at UBC was the person that suggested this, is something called cubic spline estimate. So what are cubic splines? So a spline basically, suppose I've got a bunch of points. Here they are, a bunch of points. And I want to fit a curve through those points. Well, if I've got 10 points, a 9-degree polynomial exactly goes through each point. It's really messy, it's really uneven. So one way to think about that is I could join points with the curve. I could join 2 points with the curve. I could join 3 points with a quadratic or 4 points with a cubic. And I could also do the cubic so that adjacent curves smoothly fit together. So cubic splines basically means I take a series of cubic polynomials and slide across my data and bend in such a way that they join smoothly. And that would then allow me, since I change those curves as I move, to fit rather arbitrary forms. I'm not forcing myself to fit a single maximum or minimum. It's kind of a general strategy for generally fitting curves. It's called the cubic spline. And so what Schluter did was he assumed this non-parametric, because you're not assuming a form for the function. It's actually formally called semi-parametric, because you're not assuming the shape, but you are assuming the residuals are either normal, binomial, or Poisson. And then he basically had a resampling program that basically generated the best fit. So here are examples of those. The actual ticks here are the data. Survivor, basically 0 or 1. The dashed curve here is the quadratic fit. This is the cubic spline fit. And the cubic spline fit seems to do a much better job, right? It's not quite exponential. It's got a nice thing. So again, Darwin's finches, that's one example. A second example is survivability as a function of tarsus length. Again, I've got 0, 1 data. By the way, when you have 0, 1 data, people often fit this with something called a logistic regression. And a logistic regression simply says, let's go right down here. If my length is 19.5, what's the probability I survive? So it basically figures out a p-value, sort of the average of these values in here, and that's the p-value, and that's what it basically does. But this is fitting that cubic spline. Again, you see it's got a nice pleasing shape, and it's smoother, and it's not that as jaggedy. But the famous is human birth weight. So this is a very famous study by Penrose, where they basically showed there was an optimal birth weight. And here are the data. You fit the best cubic spline through that, you clearly get an optimum. Now, the problem is you can actually ask, is this fall off here statistically significant? That is there even though the curve has a maximum, is that maximum statistically significant? Turns out it's not. So whether or not these Penrose data are correct is unclear. If you fit a cubic through that, a quadratic, you'd also get this form, but it would be wouldn't be as flat as it is here. So you see that the Dolph's semi-parametric cubic spline estimator is a way to handle fitness functions. All the ones I showed you are relatively smooth, but you can also fit things that have multiple peaks and valleys as long as your data is sufficiently dense enough. That's really the limitation on this method. So that then raises the issue of what we call generalized selection gradients. Let me remind you about that. So Fred Jansen and Michael Morrissey, they're just holding a little a sheep. He's holding, I think, an amphibian of some sort. Turtle, there you go. So close enough. It's in the water, you know. I'm a mathematician. Getting it to a tetrapod is pretty good, right? So we have these relationships that when phenotypes are normally distributed, that beta, my linear regression slope, I can write as a partial with respect to the landscape gradient, with a fitness gradient, that is the partial of the mean fitness surface. I can write it as an average curvature of the individual fitness surface. And so these expressions hold when you either have normally distributed data or your fitness function is truly a quadratic. The question is, what happens when the data are not normal and the fitness function is not quadratic? In that case, we then get different estimators for average curvature and your selection gradient over the landscape. And Jansen and Morrissey both proposed different estimators for that. So the Jansen-Stein estimator, which is cute because the James-Stein estimator is a very famous estimator in statistics. The Jansen-Stein estimator says, and I use JS down there, your average curvature is easily computed because you simply take your fitness surface and take the expected value of the curvature. If you're worried about the curvature, remember you can use numerical methods to numerically compute these derivatives. Take your current value, add a tiny value, subtract off a tiny value, divide by that tiny value. Numerically, that's an estimate of the derivative. That's the first derivative, that's the second. So if I have an arbitrary fitness function, I can still numerically compute these and then numerically compute an average gradient over that fitness surface. That's called the Jansen-Stein gradient. We can do it for average slope. We can also do it for average curvature. And I use the JS to remind you of those because now these may differ, but these here are making no assumptions about normality. Now, the issue, of course, is what do they tell you? And they just give you average curvature. They're not really that useful for predicting selection response. But nonetheless, they allow you to compute gradients, in this case, average slope and average curvature, on completely generalized fitness functions. Morrissey gradients are trying to get at this, that the gradient of log mean fitness with respect to mean, that's a magic quantity because that basically tells you how the population responds in the mean. You multiply that by the variance, and that's the general response. It's the exact response in the Landy equation. There's something called the Barton-Torelli equations, which are covered in chapter 24, where if you've got non-normal data, it tells you what happens, and the leading term is this term here multiplied by the added variance. Then there are additional terms that are functions of higher moments times things like the genomic skew and stuff. But so these things are very important in determining how the population evolves, and you compute those numerically. Because again, this is something you can also compute numerically. So if you give the computer your estimated fitness surface, it can then go in, there's your estimated fitness surface, it can then go in and numerically compute these derivatives for you. And in fact, Morrissey has a package that does this for you. So these notion of gradients, if you have the trait being normal, or you've got the true fitness function being a quadratic, you've got these relationships. So beta, which is the linear regression slope, equals the average fitness, the average curvature. It also equals the gradient with respect to log mean fitness. If you don't have normal data and your fitness function isn't a quadratic, then these equalities no longer hold. The Jansen-Stein allows you to compute this numerically, and the Morrissey also allows you to compute this numerically. These may be differ. This gives you average curvature, which is of some interest. This here gives you the term you need to predict how the character is going to change. Okay? So these are general extensions of those ideas. So those are extending gradients. We'll come back and talk about those when we talk about, again, multiple traits. So again, it's a bit of a technicality, but be aware it's out there. In case you need them, you know where you can look up the references for them and look up the details on why you use them. So Landy-Arnold is extremely powerful, but has problem number one. It's a quadratic that limits the type of things you get. You can often get incorrect fitness surfaces by forcing a quadratic fit on that. Again, we'll talk more about that tomorrow. The other problem it has is when you fit that regression, you use ordinary least squares. Ordinary least squares does not require normality. It does require homoskedastic independent residuals. So it requires something about your residual structure. Normality allows you to remove skewness and express kurtosis of the trait in specific fashions. What can you say in general then when fitnesses are not normally distributed? And the way to get at that is how we deal with non-Gaussian fitness. And a lot of the work was done, as I mentioned before, by Shaw and Geyer, and Jared Hadfield at Edinburgh, an ornithologist, has done a lot of work about more realistic models of fitness. And let's talk about a couple of models. So one model I mentioned briefly was logistic regression. Suppose I'm looking at viability selection. And what I want to do is predict the survival fraction given you have a certain trait value. Well, if I do that as a linear regression, the problem is it's easy to imagine scenarios where the survival probability is less than 0 or bigger than 1. Those aren't in the space. Is there some way I can do that to guarantee survival probabilities always fall between 0 and 1? And the answer is yes, it's logistic regression. Suppose my model is this. What I do is I take my trait value. I want to find A and B to curve fit my survival probability. And you'll notice here, this thing always lies between 0 and 1. If this thing here is exponential term is very large, that gives you 0. If this term here is very small, if this term here is, so if this term here is close to 0, that gives you 1 over 0. Basically, that gives you something that approaches, back up a second, late in the day, sorry. As this term vanishes, you get a p close to 1. As this term gets very large, you get a p close to 0. So the nice thing about this is that this can take on any value you want, and it maps into something that gives a parameter between 0 and 1. You can also then include quadratic terms. So for example, I talk about multiple traits. Well, one trait could be z. The second trait, z2, could be z1 squared. So you can actually put quadratic terms in here as well. So Jansen and Stein were the ones that really pushed logistic regression for viability data. The other nice thing about logistic regression is it allows the residuals to be binomial. The data are 0, 1. So it's a more natural form when you have 0, 1 data. So how then can we take, this is an example of something we call a generalized linear model. In generalized linear model, I have on some scale a linear function. I then map it into a parameter of interest, which we'll talk about, and then I allow it to have the residual structure I want. Maybe it's binomial, maybe it's Poisson, maybe it's exponential. So it's a much broader class of families. So we can also write this thing here by using the logit function. Those are basically equivalent. And a fun example of that is Coulson on SOA sheep data had this term in here, which is a density-dependent survival term, and also a random effect term for environment. So this expression here contains fixed effects and also contains random effects. This is called the generalized mixed linear model. So the broader way to look at this type of thing is something called a generalized linear model. And let me motivate it by the following. Suppose that each of you has a number of offspring, and that number of offspring is determined from a Poisson distribution. So it's a random term, but each of you varies in your intrinsic mean. So in the Poisson, if your mean is mu, the chance of having 0 e to the minus mu, chance of 1 is mu e to the mu, the chance of 2 is mu squared e to the minus mu over 2, etc. So the data I observe are 4 offspring, 7 offspring, 2 offspring, 1 offspring. My model could be that each of you differs. Your trait value determines the mean of this underlying Poisson, and then from that underlying Poisson, I draw a realization. So the obvious question becomes, how do I model the mean? And you can model the mean by some linear function. There's your one or more characters. You can put quadratic terms there to get, nonlinearities. But the problem with that term is when you compute what that is, if it lies between 0 and infinity, it makes sense as a mean. If it's negative, Poisson distributions don't have negative means. So what I want to do is take some way to map that linear term that can potentially range from plus to minus infinity into a parameter space where it's the accessible parameter space for means, 0 to infinity. So one easy way is to take e to that number. If that number is negative, it maps to a value near 0. If that number is positive, it maps to some value away from 0. So the idea is we have 3 scales, an underlying or latent scale, which is transformed into a value we see. So I observe 6 offspring in you. That 6 offspring arises from 2 distinct events. Number 1, you have some intrinsic value based upon traits in you. I then take that intrinsic value and map it into an expected mean of a Poisson. Then, given that expected mean of the Poisson, I sample from that and get your value. That's how these generalized linear models work. So I have an underlying latent scale, an expected data scale. So I basically take this value and translate it into expected means. Then I draw a realization from that. That gives me the observed data scale value. And this approach is called a generalized, not general, but generalized linear model. If I have some of these things be random effects, we call that a generalized linear mixed model, or GLEM. And Jared has a package for handling GLEMs that come out. So this is the approach to look at more general distributions besides a normal. And obvious candidates are a Poisson, a Bernoulli 0-1, and other type of counting distributions. So in that, let's look at some potential functions we can use. One function comes out of survival theory. And survival theory, or survival analysis, which mainly is cancer trials, you can get these double exponential fitness functions. It's got this funny form here. So it's an exponential of an exponential. This is something called the proportional hazard model. And the reason we have exponentials are exponentials have this nice feature of memorylessness. If this light bulb follows an exponential distribution, the fact that it's been on for 50 hours and that one's been on for 5 minutes, given that both of them have the same lifespan from here on out, they have this memoryless feature. And that memoryless feature allows us to handle missing data, which is why a lot of these survival models are based upon that. So for example, a simple thing here would be to assume that this risk function here is just simply log of t. So what I then simply get is that this part here becomes e to the minus lambda t. So I've got a constant risk, so my survival decays over time. And then I add on to that a factor that changes that risk relative to what my trait value is. So for example here, a constant decay, and then a value that accentuates that or retards that based upon my trait value. So that's an example of a more general type of fitness function that comes out of survival analysis. So you can potentially use that class of functions. The other class you can have is to realize that fitness data comes in a couple of forms, basically numbers. 0, 1, alive, dead, flowered, not flowered, or counting, 1 mate, 2 mate, 3 mates, 17 offspring, 19 offspring, 54 offspring. That gives you a couple of different types of distributions you can use. So you can have a Bernoulli, which is basically 0, 1, alive, dead. That has a parameter p. You can estimate p with a general model. You can have a Poisson. The Poisson, you've got to specify what the mean of that Poisson is as a function of your trait value. Again, you can estimate that. And you can estimate that by basically taking the log, fitting this function, taking e to that, and then that gives you the mean. It's called a log linear model. These models have Poisson data. Or you can have other features. One problem with the Poisson is you often have data which are over-dispersed. In the Poisson, the mean should equal the variance. Very often your data are over-dispersed. The mean is bigger than the variance. There's two reasons for that. Number one, excess of values of 0, and the rest of it follows the Poisson. Number two, the data don't follow the Poisson. So one way to handle over-dispersion without worrying about 0 is to use a negative binomial distribution. There is a negative binomial. You can then ask what the mean is. There's the variance. What you can see is the mean over variance ratio is bigger than 1, and basically adjust for these parameters. So you can use negative binomial distributions to handle over-dispersed data, and I give some examples of where people have done that. The other possibility is 0 truncated or 0 inflated distributions. Think about flowering. I either flower or don't flower. If I flower, maybe I follow Poisson. So one way to handle that is a Bernoulli random variable, flower or don't flower, then condition on flowering, I have a Poisson where the value is 1 or larger. So we call that 0 truncated. Here's what it looks like. That's my value of getting J observations given Z. This basically removes the probability mass at 0. And so, for example, here is what a 0 truncated Poisson looks like. This basically says that I allow values of 1 or larger. You can also truncate the first K. Ruth has an example of those come up occasionally. So you can take a distribution and remove 0 and assume you've got the rest of that form once you get above 0. You can also do the opposite, which is 0 inflated. You can take that distribution and you can add an extra probability mass at 0. Right? So 0 inflated is like doing a Bernoulli on yes, no, and then your distribution on yes. 0 inflated kind of does both those together. These are actually very similar, 0 inflated and 0 truncated. With 0 truncated, you have to have a separate probability that tells you how much is 0. So basically, these are ways to handle realistic data. Realistic fitness data have a big point mass at 0 because lots of individuals don't reproduce. Realistic fitness data often have Bernoulli, survive, don't survive, flower, don't flower. They often have Poisson-like, which is 1 mate, 2 mate, 3 mates. So for example, you might be offspring, yes or no. That's a Bernoulli. If the answer is yes, then you have a truncated Poisson. So 1 or more offspring, or a negative binomial. Those are distributions you can fit. So in an Astra model here, for example, your survival to stage 1 is a Bernoulli. So you could model that, for example, with survival analysis. Same thing here, same thing there. Those may be different values. This is flowering. That's yes, no. That's Bernoulli, that's Bernoulli, that's Bernoulli. Again, those could have different values that depend upon your trait. You can estimate that. And given you flower, you've got 1 or more. So these basically would be 0 truncated Poissons, or even zero truncated negative binomials, where again, the success parameters depend upon the trait values and you estimate them. So the software for Astra models, you specify your life history graph, you specify the distributions, then it go ahead and tries to fit those distributions. So to give you some idea, again, they're called Astra because they come out of the purple coneflower. Simplest life history graph is your observation goes to a fitness value. If Z is normally distributed, that's a linear model, Landy-Arnold estimation. If Z is Bernoulli, live dead, that's logistic regression. If Z is Poisson, that's a log linear model. I basically use a linear model and then take the exponent of that to give me a mean. I then draw from that. If my graph is individual goes to X, goes to Y, or X is Bernoulli, and Y is either zero truncated, Poisson, or negative binomial, this corresponds to zero inflated versions, because basically to get here, you've got to have at least one, and this is given you have at least one. A graph like this would be survival analysis. So the point is, these Astra models are very, very flexible and allow for very different types of distributions on them. It's formally, let me hit the wording up here. No, I don't have it. It's a random forest graph exponential model family. So it's the path analysis part here shows the flow of the various fitness stages. But path analysis is a regression approach where you simply put correlation coefficients on there. The Astra model says that's your underlying model structure. Then you put probability distributions on there, and then Astra does the bookkeeping to then give you the final probability distributions. So for this data, your probability distribution for the overall fitness is simply the sum of those three. Those are the number of flower heads. That's your surrogate measure of lifetime reproductive success. And so, for example, if you think about what those are, so that's to get to here, you've got a zero truncated Poisson where the mass at zero depends upon these survival probabilities. You've got another zero truncated Poisson where the mass here depends upon that survival and flower possibilities. You've got a third zero truncated where the mass at zero depends upon that step and flowering at 3. And the Astra models basically put all those together and return the proper form of the distribution for you. So that's what they do. So Astra models are extremely powerful, but as you see, there's a lot of details. So what's the big picture? The big picture is Landy-Arnold framework was a great way to start. It basically assumed you had so many offspring. Yeah, the normal approximation is not that bad. Real fitness data is different. Real fitness data, you've got a lot of individuals with value 0, and then you've got individuals that take discrete values after that. That's not a normal. And even in this relatively simple life history, that's not even a standard distribution, because basically it's a weighted sum of 3 different zero truncated. So you have different weights at 0 and different weights to truncate it. What does that look like? Well, the Astra model framework allows you to build those up, and the Astra model software allows those parameters to be functions of your observations. So they change with the observations. So survivability or flowering may change with the height of the plant or the mass of the plant or some trichome character. And the Astra model framework then allows you to basically take the better model for the residual structure and go ahead and fit the data on that. And there's software that does that for you. So a lot of detail there, but the overall picture is fitness data is compromised because it's not normal. Usually it's got a bunch of inflated zeros, and then it's got some funky truncated distribution, and it's often the sum of those. How do you get that distribution? The Astra models will give that for you. And again, so named because they're working on an Astra. So a lot of kind of technical stuff at the end here. Great way to end the day. All this exciting things. You just can't wait to look them up. But again, the way to think about these is I'm giving you kind of an overview and a roadmap. If you're going to make a trip, you know where the roadmap is. You go look up the roadmap and read about these and then start the journey, right? So questions or comments at the end of the day today? No questions or comments? Yeah. So the way to think about that's a good way to think about this is you have a population. You've done Landy Arnold on that population. This is just Landy Arnold on steroids. So you've got estimates of fitness parameters in there. You got estimates of standard errors. You can then ask how stable those are over environments and things of that nature. So don't get, overly worried about the detailed structure. Just think of this as another. So imagine the net result here is you get a quadratic function that basically tells you what your expected fitness should be. It's kind of complicated, but it's a quadratic function. That's a Landy Arnold. Then you can look at the slopes on those, which show you how certain traits influence fitness, and look at those slopes for those same traits in some of their population or some of their time or some of their season are different. That's how you can apply these. Okay. I think you need either a heavy drink or a good sleep. But the good news is we have 2 more lectures left, and they won't be any more difficult than this one. You notice I gave you an opportunity for difficulty. I gave you an upper bound. I didn't say where they'd actually be, but they won't be more difficult than these.